Hello and welcome to this lecture. In this lecture, we look at daemon sets in Kubernetes. So far, we have deployed various pods on different nodes in our cluster. With the help of replica sets and deployments, we made sure multiple copies of our applications are made available across various different worker nodes. Daemon sets are like replica sets, as in it helps you deploy multiple instances of pods, but it runs one copy of your pod on each node in your cluster. Whenever a new node is added to the cluster, a replica of the pod is automatically added to that node, and when a node is removed, the pod is automatically removed. The daemon set ensures that one copy of the pod is always present in all nodes in the cluster. So what are some use cases of daemon sets? Say you would like to deploy a monitoring agent or log collector on each of your nodes in the cluster so you can monitor your cluster better. A daemon set is perfect for that, as it can deploy your monitoring agent in the form of a pod in all the nodes in your cluster. Then you don't have to worry about adding or removing monitoring agents from these nodes when there are changes in your cluster, as the daemon set will take care of that for you. Earlier, while discussing the Kubernetes architecture, we learned that one of the worker node components that is required on every node in the cluster is a kube proxy. That is one good use case of daemon sets. The kube proxy component can be deployed as a daemon set in the cluster. Another use case is for networking. Networking solutions like ViVNet requires an agent to be deployed on each node in the cluster. We will discuss about networking concepts in much more detail later during this course, but I just wanted to point it out here for now. Creating a daemon set is similar to the replica set creation process. It has nested pod specification under the templates section and selectors to link the daemon set to the pods. A daemon set definition file has a similar structure. We start with the API version, kind, metadata, and spec. The API version is apps v1, kind is daemon set instead of replica set. We will set the name to monitoring daemon. Under spec, you have a selector and a pod specification template. It's almost exactly like the replica set definition, except that the kind is a daemon set. Ensure the labels in the selector matches the ones in the pod template. Once ready, create the daemon set using the kubectl create daemon set command. To view the created daemon set, run the kubectl get daemon set command. And of course, to view more details, run the kubectl describe daemon set command. So how does a daemon set work? How does it schedule pods on each node? And how does it ensure that every node has a pod? If you were asked to schedule a pod on each node in the cluster, how would you do it? In one of the previous lectures in this section, we discussed that we could set the node name property on the pod to bypass the scheduler and get the pod placed on a node directly. So that's one approach. On each pod, set the node name property in its specification before it is created, and when they are created, they automatically land on the respective nodes. So that's how it used to be until Kubernetes version 1.12. From version 1.12 onwards, the daemon set uses the default scheduler and node affinity rules that we learned in one of the previous lectures to schedule pods on nodes. Well, that's it for this lecture. Head over to the practice test and practice working with daemon sets. Hello and welcome to this lecture. In this lecture, we discuss about static pods in Kubernetes. Earlier in this course, we talked about the architecture and how the kubelet functions as one of the many control plane components in Kubernetes. The kubelet relies on the kube API server for instructions on what pods to load on its node, which was based on a decision made by the kube scheduler, which was stored in the etcd data store. What if there was no kube API server and kube scheduler and no controllers and no etcd cluster? What if there was no master at all? What if there were no other nodes? What if you're all alone in the sea by yourself, not part of any cluster? Is there anything that the kubelet can do as the captain on the ship? Can it operate as an independent node? If so, who would provide the instructions required to create those pods? Well, the kubelet can manage a node independently. On the ship host, we have the kubelet installed. And of course, we have Docker as well to run containers. There is no Kubernetes cluster, so there are no kube API server or anything like that. The one thing that the kubelet knows to do is create pods. But we don't have an API server here to provide pod details. By now, we know that to create a pod, you need the details of the pod in a pod definition file. But how do you provide the pod definition file to the kubelet without a kube API server? You can configure the kubelet to read the pod definition files from a directory on the server designated to store information about pods. Place the pod definition files in this directory. The kubelet periodically checks this directory for files, reads these files, and creates pods on the host. Not only does it create the pod, it can ensure that the pod stays alive. If the application crashes, the kubelet attempts to restart it. If you make a change to any of the file within this directory, the kubelet recreates the pod for those changes to take effect. If you remove a file from this directory, the pod is deleted automatically. So these pods that are created by the kubelet on its own without the intervention from the API server or rest of the Kubernetes cluster components are known as static pods. Remember, you can only create pods this way. You cannot create replica sets or deployments or services by placing a definition file in the designated directory. They're all concepts part of the whole Kubernetes architecture that requires other cluster plane components like the replication and deployment controllers, etc. The kubelet works at a pod level and can only understand pods, which is why it is able to create static pods this way. So what is that designated folder and how do you configure it? It could be any directory on the host, and the location of that directory is passed in to the kubelet as an option while running the service. The option is named pod manifest path, and here it is set to etc kubernetes manifest folder. There's also another way to configure this. Instead of specifying the option directly in the kubelet.service file, you could provide a path to another config file using the config option and define the directory path as static pod path in that file. Clusters set up by the kubeadmin tool uses this approach. If you're inspecting an existing cluster, you should inspect this option of the kubelet to identify the path to the directory. You will then know where to place the definition file for your static pods. So keep this in mind when you go through the labs. You should know to view and configure this option irrespective of the method used to set up the cluster. First, check the option pod manifest path in the kubelet service file. If it's not there, then look for the config option and identify the file used as the config file. And then within the config file, look for the static pod path option. Either of these should give you the right path. Once the static pods are created, you can view them by running the docker ps command. So why not the kubecontrol command as we have been doing so far? Remember, we don't have the rest of the Kubernetes cluster yet. So the kubecontrol utility works with the kube API server. Since we don't have an API server now, no kubecontrol utility, which is why we're using the docker command. So then how does it work when the node is part of a cluster? When there is an API server requesting the kubelet to create pods, can the kubelet create both kinds of pods at the same time? Well, the way the kubelet works is it can take in requests for creating pods from different inputs. The first is through the pod definition files from the static pods folder, as we just saw. The second is through an HTTP API endpoint. And that is how the kube API server provides input to kubelet. The kubelet can create both kinds of pods, the static pods and the ones from the API server, at the same time. Well, in that case, is the API server aware of the static pods created by the kubelet? Yes, it is. If you run the kubecontrol get pods command on the master node, the static pods will be listed as any other pod. Well, how is that happening? When the kubelet creates a static pod, if it is a part of a cluster, it also creates a mirror object in the kube API server. What you see from the kube API server is just a read-only mirror of the pod. You can view details about the pod, but you cannot edit or delete it like the usual pods. You can only delete them by modifying the files from the node's manifest folder. Note that the name of the pod is automatically appended with the node name, in this case, node 01. So then, why would you want to use static pods? Since static pods are not dependent on the Kubernetes control plane, you can use static pods to deploy the control plane components itself as pods on a node. Well, start by installing kubelet on all the master nodes, then create pod definition files that uses Docker images of the various control plane components, such as the API server, controller, etcd, etc. Place the definition files in the designated manifest folder, and the kubelet takes care of deploying the control plane components themselves as pods on the cluster. This way, you don't have to download the binaries, configure services, or worry about the services crashing. If any of these services were to crash, since it's a static pod, it will automatically be restarted by the kubelet. Neat and simple. That's how the kube admin tool sets up a Kubernetes cluster. Which is why when you list the pods in the kube system namespace, you see the control plane components as pods in a cluster setup by the kube admin tool. We will explore that setup in the upcoming practice test. Before I let you go, one question that I get often is about the difference between static pods and daemon sets. Daemon sets, as we saw earlier, are used to ensure one instance of an application is available on all nodes in the cluster. It is handled by a daemon set controller through the kube API server, whereas static pods, as we saw in this lecture, are created directly by the kubelet without any interference from the kube API server or rest of the Kubernetes control plane components. Static pods can be used to deploy the Kubernetes control plane components itself. Both static pods and pods created by daemon sets are ignored by the kube scheduler. The kube scheduler has no effect on these pods. Well, that's it for this lecture. Head over to the practice test and practice working with static pods.
Hello and welcome to this lecture. In this lecture, we look at deploying multiple schedulers in a Kubernetes cluster. Now, we have seen how the default scheduler works in Kubernetes in the previous lectures. It has an algorithm that distributes pods across nodes evenly, as well as takes into consideration various conditions we specify through taints and tolerations and node affinity, etc. But what if none of these satisfies your needs? Say you have a specific application that requires its components to be placed on nodes after performing some additional checks. So you decide to have your own scheduling algorithm to place pods on nodes so that you can add your own custom conditions and checks in it. Kubernetes is highly extensible. You can write your own Kubernetes scheduler program, package it and deploy it as the default scheduler or as an additional scheduler in the Kubernetes cluster. That way, all of the other applications can go through the default scheduler. However, some specific applications that you may choose can use your own custom scheduler. So your Kubernetes cluster can have multiple schedulers at a time. When creating a pod or a deployment, you can instruct Kubernetes to have the pod scheduled by a specific scheduler. So let's see how that's done. Now, when there are multiple schedulers, they must have different names so that we can identify them as separate schedulers. So the default scheduler is named default scheduler, and this name is configured in a cube scheduler configuration file that looks like this. Now the default scheduler doesn't really need one, because if you don't specify a name, it sets the name to a default scheduler. But this is how it would look if you were to create one. And for the other schedulers, we could create a separate configuration file and set the scheduler name like this. So let's start with the most simplest way of deploying an additional scheduler. Now, earlier we saw how to deploy the Kubernetes kube scheduler. We download the kube scheduler binary and run it as a service with a set of options. Now, to deploy an additional scheduler, you may use the same kube scheduler binary, or use one that you might have built for yourself, which is what you would do if you needed the scheduler to work differently. In this case, we're going to use the same binary to deploy the additional scheduler, and this time we point the configuration to the custom configuration file that we created. So each scheduler uses a separate configuration file, and with each file having its own scheduler name. And note that there are other options to be passed in, such as the kubeconfig file to authenticate into the Kubernetes API, but I'm just skipping that for now just to keep it super simple. This is not how you would deploy a custom scheduler 99% of the time today, because with kubeadm deployment, all the control plane components run as a pod or a deployment within the Kubernetes cluster. So let's look at another way. So let's look at how it works if you were to deploy the scheduler as a pod. So we create a pod definition file and specify the kubeconfig property, which is the path to the scheduler conf file that has the authentication information to connect to the Kubernetes API server. We then pass in our custom kube scheduler configuration file as a config option to the scheduler. Note that we have the scheduler name specified in the file, so that's how the name gets picked up by the scheduler. Now, another important option to look here is the leader elect option, and this goes into the kube scheduler configuration. The leader elect option is used when you have multiple copies of the scheduler running on different master nodes, as in a high availability setup where you have multiple master nodes with the kube scheduler process running on both of them. If multiple copies of the same scheduler are running on different nodes, only one can be active at a time. And that's where the leader elect option helps in choosing a leader who will lead the scheduling activities. So we will discuss more about HA setup in another section. In case you do have multiple masters, just remember that you can pass in this additional parameter to set a log object name. And this is to differentiate that the new custom scheduler from the default election process. Now let's take a look at how to deploy the additional scheduler as a deployment. And for this, I'm going to go into the Kubernetes documentation pages and for the one for configuring multiple schedulers. And if you look here, first of all, it shows you how to, if you were to build your own scheduler, how you could clone the Kubernetes repo and then make changes to the kube scheduler and build it and package it into a Docker image. And then here you can see the config file to create a scheduler as a deployment. You can ignore all of this to begin with. So this is what it is really. So here you have the deployment, and this deployment is similar to the pod, but it's just that it's a deployment. The pod that we just looked at, but it's just that it's a deployment. So here you have the image, which is the custom kube scheduler image. And this is the config file that we just talked about, which has your custom my scheduler config file, right? And the binary is the kube scheduler binary. Now, for this to work, there are some additional kind of prerequisites. So some of these are like the service account and cluster role bindings. And these are basically for authentication, right? And we discussed about cluster role bindings and cluster roles and service accounts in the auth section. So if you haven't gone through that yet, just hold off on this. You can basically ignore this for now. And the only other thing is how this file is passed into the deployment, right? So you can either create this file locally and then pass it in as a volume mount, as it's done for the other pods usually. Or another thing you could do that's done here, the approach that's used here is basically creating a config map. So this is the kube scheduler configuration that we just talked about with the leader elect option set to false, because I think the replicas is just one. And then you have the scheduler name here. So this is the config file, and then this config file is passed in as a volume here, as a as a config file. So basically, whatever is the contents in that particular config map is then mapped to a volume mount, to a volume here, which is this specific location, and then from this location you have this YAML file which basically has this content, right? So this is how that maps. But again, if you haven't gone through the volume and volume mount sections of this course, then just hold off on this for now, and you'll understand that when we talk about these. And then again, liveness probes, readiness probes, resources, and security context, all of these are sections that we talk about later. So again, you can ignore these for now. But what we need to understand here is just that this section on how this is passed, this file is passed to this custom scheduler. Okay, so yep, that's about that. So just proceeding with our lecture. So when you run the get pods command in the kube system namespace, you can then see the new custom scheduler running. So this is if you run it as a pod, and if you run it as a deployment, then you'll probably see a slightly different naming convention, but you'll be able to see the pod there. Just make sure you're checking the right namespace. Now, once we have deployed that custom scheduler, the next step is to configure a pod or a deployment to use this new scheduler. So how do you use that our custom scheduler? So here we have a pod definition file, and what we need to do is add a new field called scheduler name and specify the name of the new scheduler, and that's basically it. This way, when the pod is created, the right scheduler gets picked up and the scheduling process works. Now, we now create the pod using the kubectl create command. Now, if the scheduler was not configured correctly, then the pod will continue to remain in a pending state. And if everything is good, then the pod will be in a running state. So if the pod is in a pending state, then you can look at the logs on the pod under the pod describe command, the kubectl describe command, and you'll mostly notice that the scheduler isn't configured correctly. Now, how do you know which scheduler picked it up? So we have multiple schedulers. How do you know which scheduler picked up scheduling a particular pod? Now, we can view this in the events using the kubectl get events command with the -o wide option. And this will list all the events in the current namespace and look for the scheduled events. And as you can see, the source of the event is the custom scheduler that we created. That's the name that we gave to the custom scheduler. And the message says that it's successfully assigned the image. So that indicates that it's working. Now, you could also view the logs of the scheduler in case you run into issues. So for that, view the logs using the kubectl logs command and provide the scheduler name, either the pod name or the deployment name, and then the right namespace. Well, that's it for this lecture, and I'll see you in the next one. Let us now look at what scheduler profiles are. So let's first recap how the Kubernetes scheduler works, using this simple example of scheduling a pod to one of these 4 nodes that you can see here that are part of the Kubernetes cluster. So here we have our pod definition file, and there's our pod. It is waiting to be scheduled on one of these 4 nodes. Now, it has a resource requirement of 10 CPU. So it's only going to be scheduled on a node that has 10 CPU remaining. And you can see the available CPU on all of these nodes that are listed here. Now, it is not alone. There are some other pods that are waiting to be scheduled as well. So the first thing that happens is that when these pods are created, the pods end up in a scheduling queue. So this is where the pods wait to be scheduled. So at this stage, pods are sorted based on the priority defined on the pods. So in this case, our pod has a high priority set. So to set a priority, you must first create a priority class that looks like this. And you should set it a name and set it a priority value. In this case, it's set to 1 million. So that's really high priority. So this is how pods with higher priority gets to the beginning of the queue to be scheduled first. And so that sorting happens in this scheduling phase. Then our pod enters the filter phase. This is where nodes that cannot run the pod are filtered out. So in our case, the first two nodes do not have sufficient resources, so do not have 10 CPU remaining, so they are filtered out. The next phase is the scoring phase. So this is where nodes are scored with different weights. From the two remaining nodes, the scheduler associates a score to each node based on the free space that it will have after reserving the CPU required for that pod. So in this case, the first one has 2 left and the second node will have 6 left. So the second node gets a higher score. And so that's the node that gets picked up. And finally, in the binding phase, this is where the pod is finally bound to a node with the highest score. Now, all of these operations are achieved with certain plugins. For example, while in the scheduling queue, it's the priority sort plugin that sorts the pods in an order based on the priority configured on the pods. This is how pods with priority class gets higher priority over the pods, other pods when scheduling. In the filtering stage, it's the node resources fit plugin that identifies the nodes that has sufficient resources required by the pods and filters out the nodes that doesn't. Now, some other plugin examples that come into this particular stage are the node name plugin that checks if a pod has a node name mentioned in the pod spec and filters out all the nodes that does not match this name. Another example is the node unschedulable plugin that filters out nodes that has the unschedulable flag set to true. So this is when you run the the cordon command on a node, which we will discuss later. But all the nodes that has the unschedulable flag set to true, it's this particular plugin that makes sure that no pods are set on those nodes. Now, in the scoring phase, again, the node resources fit plugin associates a score to each node based on the resource available on it, and after the pod is allocated to it. So as you can see, a single plugin can be associated in multiple different phases. Another example of a plugin in this stage would be the image locality plugin that associates a high score to the nodes that already has the container image used by the pods among the different nodes. Now note that at this phase, the plugins do not really reject the pod placement on a particular node. For example, in case of the image locality node, it ensures that pods are placed on a node that already has the image, but if there are no nodes available, it will anyway place the pod on a node that does not even have the image. So it's just a scoring that happens at this stage. And finally, in the binding phase, you have the default binder plugin that provides the binding mechanism. Now, the highly extensible nature of Kubernetes makes it possible for us to customize what plugins go where, and for us to write our own plugin and plug them in here. And that is achieved with the help of what is called as extension points. So at each stage, there is an extension point to which a plugin can be plugged to. In the scheduling queue, we have a queue sort extension to which the priority sort plugin is plugged to. And then we have the filter extension, the score and the bind extension to which each of these plugins that we just talked about are plugged to. As a matter of fact, there's more. So there are extensions before entering the filter phase called the pre-filter extension, and after the filter phase called post-filter. And then there are pre-score before the score extension point, and reserve after the extension point, the score extension point. And then there is permit and pre-bind before the bind, and post-bind after the binding phase. So, so there are so many options available. Basically, you can get a custom code of your own to run anywhere in these points by just creating a plugin and plugging it into the respective kind of point that you want to plug it to. And here is a little bit more details on some additional plugins that come by default that are associated with the different extension points. As you can see, some of the plugins span across multiple extension points. Some of them are just within a specific extension point. So that's what scheduling plugins and extension points are. So the highly extensible nature of Kubernetes allows us to customize the way that these plugins are called and write our own scheduling plugin if needed. So having learned that, let's look at how we can change the default behavior of how these plugins are called, and how we can get our own plugins in there if it's really needed. So taking a step back, earlier we talked about deploying 3 separate schedulers, each with a separate scheduler binary. So we have the default scheduler, and then the my scheduler, and then the my scheduler 2. Now all of these are 3 separate scheduler binaries that are run with a separate scheduler config file associated with each of them. Now that's one way to deploy multiple schedulers. Now the problem here is that since these are separate processes, there is an additional effort required to maintain these separate processes, and also more importantly, since they are separate processes, they may run into race conditions while making scheduling decisions. For example, one scheduler may schedule a workload on a node without knowing that there's another scheduler scheduling a workload on that same node at the same time. So with the 1.18 release of Kubernetes, a feature to support multiple profiles in a single scheduler was introduced. So now you can configure multiple profiles within a single scheduler in the schedule configuration file by adding more entries to the list of profiles, and for each profile specify a separate scheduler name. So this creates a separate profile for each scheduler, which acts as a separate scheduler itself, except that now multiple schedulers are run in the same binary as opposed to creating separate binaries for each scheduler. Now, how do you configure these different scheduler profiles to work differently? Because right now all of them just simply have different names. So they're going to work just like the default scheduler. How do you configure them to work differently? Under each scheduler profile, we can configure the plugins the way we want to. For example, for the My Scheduler 2 profile, I'm going to disable certain plugins like the taint and toleration plugin and enable my own custom plugins. For the My Scheduler 3 profile, I'm going to disable all the pre-score and score plugins. So this is how that's going to look. Under the plugin section, specify the extension point and enable or disable the plugins by name or a pattern as shown in this case. So yeah, so that's about it. I hope that gives you an overview of how schedulers and scheduler profiles work and how you can configure multiple scheduler profiles in Kubernetes. To read more about this, check out the Kubernetes enhancement proposal that introduced multi-scheduling profiles. It's the KEP 1451 that introduced the multi-scheduling profiles, and the article on scheduling framework. Well, that's all for now. I will see you in the next one.
Hello there. In this section, we discuss about the various logging and monitoring options available. We first see how to monitor the Kubernetes cluster components, as well as the applications hosted on them. We then see how to view and manage the logs for the cluster components, as well as the applications. We practice what we learn through a set of fun and challenging exercises. Well, I hope you like the upcoming lectures and practice tests, so let's get started. Hello and welcome to this lecture. In this lecture, we talk about monitoring a Kubernetes cluster. So how do you monitor resource consumption on Kubernetes? Or more importantly, what would you like to monitor? I'd like to know node-level metrics such as the number of nodes in the cluster, how many of them are healthy, as well as performance metrics such as CPU, memory, network, and disk utilization, as well as pod-level metrics such as the number of pods and the performance metrics of each pod, such as the CPU and memory consumption on them. So we need a solution that will monitor these metrics, store them, and provide analytics around this data. As of this recording, Kubernetes does not come with a full-featured built-in monitoring solution. However, there are a number of open source solutions available today, such as Metrics Server, Prometheus, the Elastic Stack, and proprietary solutions like Datadog and Dynatrace. Heapster was one of the original projects that enabled monitoring and analysis features for Kubernetes. You will see a lot of reference online when you look for reference architectures on monitoring Kubernetes. However, Heapster is now deprecated, and a slimmed-down version was formed known as the Metrics Server. You can have one metrics server per Kubernetes cluster. The Metrics Server retrieves metrics from each of the Kubernetes nodes and pods, aggregates them, and stores them in memory. Note that the Metrics Server is only an in-memory monitoring solution and does not store the metrics on the disk. And as a result, you cannot see historical performance data. For that, you must rely on one of the advanced monitoring solutions we talked about earlier in this lecture. So how are the metrics generated for the pods on these nodes? Kubernetes runs an agent on each node known as the kubelet, which is responsible for receiving instructions from the Kubernetes API master server and running pods on the nodes. The kubelet also contains a subcomponent known as the cAdvisor or Container Advisor. cAdvisor is responsible for retrieving performance metrics from pods and exposing them through the kubelet API to make the metrics available for the metrics server. If you're using Minikube for your local cluster, run the command minikube add-ons enable metrics-server. For all other environments, deploy the metrics server by cloning the metrics server deployment files from the GitHub repository, and then deploying the required components using the kubectl create command. This command deploys a set of pods, services, and roles to enable metrics server to poll for performance metrics from the nodes in the cluster. Once deployed, give the metrics server some time to collect and process data. Once processed, cluster performance can be viewed by running the command kubectl top node. This provides the CPU and memory consumption of each of the nodes. As you can see, 8% of the CPU on my master node is consumed, which is about 166 millicores. Use the kubectl top pod command to view performance metrics of pods in Kubernetes. Well, that's it for this lecture. Head over to the coding exercises section and practice viewing performance metrics on the Kubernetes cluster. Thank you. Hello and welcome to this lecture. In this lecture, we will talk about various logging mechanisms in Kubernetes. Let us start with logging in Docker. I run a Docker container called Event Simulator, and all that it does is generate random events simulating a web server. These are events streamed to the standard output by the application. Now, if I were to run the Docker container in the background in a detached mode using the -d option, I wouldn't see the logs. If I wanted to view the logs, I could use the docker logs command followed by the container ID. The -f option helps us see the live log trail. Now back to Kubernetes. We create a pod with the same Docker image using the pod definition file. Once the pod is running, we can view the logs using the kubectl logs command with the pod name. Use the -f option to stream the logs live, just like the Docker command. Now these logs are specific to the container running inside the pod. As we learned before, Kubernetes pods can have multiple Docker containers in them. In this case, I modify my pod definition file to include an additional container called image processor. If you run the kubectl logs command now with the pod name, which container's logs would it show? If there are multiple containers within a pod, you must specify the name of the container explicitly in the command. Otherwise, it would fail asking you to specify a name. In this case, I will specify the name of the first container, Event Simulator, and that prints the relevant log messages. Now that is the simple logging functionality implemented within Kubernetes. And that is all that an application developer really needs to know to get started with Kubernetes. And that is all you really need to know as part of the certification program. Well, that's it for this lecture. Head over to the coding exercises section and practice working with logs. Thank you.